Hello everyone, I'm Sayishnu Manohar, presenting my tech talk on basic electrical engineering. I'm from class CSCB. The topic I've selected for a tech talk on basic electrical engineering is high performance GPU tensor completion with tubal sampling pattern. Now we come to the contents. The contents are abstract, introduction, notations, definitions, tensors, result, conclusion, and references. Now we move on to the abstract. Data completion is a problem of filling missing or unobserved elements of partially observed datasets. Data completion algorithms have received wide attention and achievements in diverse domains, including data mining, signal processing, and computer vision. We observed a ubiquitous tubal sampling pattern in big data and Internet of Things (IoT) applications. GPU element sampling tensor completion in the CU tensor tubal library and GPU high performance matrix completion, respectively. With a 50% sampling rate, the proposed GPU tensor completion achieves a recovery error of 1.40 E bar 5, which is comparable with that of the GPU elements. Introduction. In big data era, tremendous volume of data are produced every day. Processes for research, industrial, manufacturing, and business intelligence data completion methods are employed to fill missing and unobserved region. Many big data or IoT applications, such as RF fingerprinting based indoor localization systems. The ubiquitous tubal sampling pattern is diverse application call for fast and accurate data completion implementation process in real time. This is the example we used RF fingerprinting using IoT, which is one of the application of tensor using GPU. Notations. We denote scalars with lowercase normal letters, vectors with bold lowercase letters. Matrices are denoted by bold face capital letters. Columns of a matrix are denoted by bold face lower letters with a subscript. Entries of a matrix are denoted by or tensor are denoted by lowercase letters with subscripts. Example Aij, meaning the entry with row index I and column index j in a particular matrix. We frequently use subset I, j to denote the meaning of indices, and with some of the notations, we will use ij to denote the index upper bounds. High order tensors are also denoted with calligraphic uppercase letters. Definition. The discrete Fourier transform DFT of a vector x belongs to R and N is a matrix vector of product y is equal to f and x, where DFT matrix Fn is equal to Fkj belongs to R is in the order n by n defined by Fkj is equal to omega n to k minus 1 into j minus 1 with omega n is equal to exponent minus 2 into pi into I into n is equal to 2 cos pi into n minus I sine 2 pi n. The identity tensor I belongs to R of order n1 into n2 into n3 is defined to be a tensor whose first frontal slice I is the n1 by n2 identity matrix and all the other frontal slices I is equal to 2 and so on n3 are 0. Orthogonal tensor. A tensor A belongs to R of order n1, n2, n3 is orthogonal if it satisfies A transpose into A is equal to A into A transpose is equal to I, where transpose means exchanging the row elements into column elements. The inverse of tensor A belongs to R of order n1 into n2 into n3 is written as A power minus 1, satisfying A inverse into A is equal to A into A inverse is equal to I, where I defines both inverse and orthogonal as identity matrix. Tensors. A tensor completion based on CP decomposition, where CP expands as candy comb and parafact. Decomposition is a powerful tool for data analysis. Verma et al. Proposed a CP-weighted optimization algorithm to estimate the missing value of a tensor. The CP decomposition of a tensor A belongs to R of order n1, n2, and so on n is given by A is equal to xli is equal to a1 into I to a2 into I and so on an into I, where an belongs to I belongs to R, denotes the outer product of the vector. It consists of decomposition of a given tensor as sum of lowest possible rank 1 tensors. A CP rank is defined by the minimum number of rank 1 terms in CP decomposition. Tensor completion based on CP decomposition. Here is a full tensor which is randomized to Canticope and Parafact, which results in compressed tensor. Here is deterministic CP, Canticope and Parafact, which denote into full rank 1 components, where compressed tensor recovers, which denotes into full rank 1 components. Tensor completion based on Tucker decomposition. Tucker decomposition is an unsupervised multi-way data analysis method, and it can be considered as the high-order principal component analysis. Tan et al. Proposed a Tucker decomposition based on method to estimate missing value of a tensor. The basic idea of the Tucker decomposition is to decompose a tensor into a small core tensor multiplied by a factor matrix along each mode. The Tucker decomposition of nth order tensor A belongs to R of order I1, I2, I3, and so on In can be written as a tensor Ia into I, 2A into 2, and so on Na into N. This is an example of a tensor completion based on Tucker decomposition. There's a raw tensor data, which when noise reduced and data compressed, which results into Tucker representation, which is further divided into non-negative CPD, non-negative Tucker decomposition. Tensor completion based on tensor singular value decomposition. Zhang and Aaron considered sampling and recovery for a three-way tensor using tensor singular value decomposition, abbreviated as tensor SVD, in which it uses T product defining the multiplication action. The tensor SVD of a tensor A belongs to R of order I1, I2, I3 is given by A is equal to U into S into VT. Results. In this subsection, we first present the simulation results of an error ratio comparison and then present the recovery computation time comparison. We use real traffic data and simulated data respectively to compare the observed error ratio under different sample ratios. In all subfigures, we found that observed error ratios of the four schemes are all under 14 into 10 to 4. It's a very small value. These results demonstrate that all schemes can achieve a good observed ratio performance in both real traffic data and simulated data experiments. Moreover, compared to TSVD or TCUR has almost same observed error at different sampling rates. These results demonstrate that our TCUR scheme is instrumental on achieving observed error ratio performance as good TSVD. Conclusion. In this paper, we formulated the missing data recovery problem of a three-way tensor as a tensor completion problem. We proposed a novel tensor completion algorithm to quickly recover the missing data of limited samples. Compared with other methods in literature, our algorithm can achieve a very good recovery performance based on observed error ratio, recovery error ratio, and computation time. References. These were ideated by E. Sechtek, M.A. Rothfuss, M.L. Jimble, and M.H. Mickle. Comparative analysis of compressive sensing approaches for recovery of missing samples in implantable wireless Doppler devices, which is IET devices signal process, consists in volume 8, number 3, page number varying from 230 to 288, established in the year 2014. S.K. Perapu and A.K. Tangirala mentioned reconstruction of missing data using compressed sensing techniques with adaptive dictionary process control. Contains in volume 47, page varying from 175 to 190, established in November 2016. That's it. Thank you for being with me. Hope you enjoyed my presentation. Thank you very much. This is Aishnu Manohar from CSCB presenting my basic electrical engineering tech talk. Thank you.